In the lecture, sorry.
Yes, please.
You mentioned that this structural software.
Yes, SAP and ETABS.
Connected with the Revit. I don't think so. That it's manually.
No. That is there's for Autodesk Revit. There is already a tool called Robot Structures. That is already inbuilt with
that. Robot is the same.
Yes,
company.
and then for SAP and ETABS, there are extensions that we use.
Extension, but when I was using this game in the industry,
Okay.
in the last year,
Revit, you mean? Revit.
Revit and SAP and ETABS.
Okay.
The robot is not that popular in Middle East. I was not in Middle East. So they have Revit is the, of course, everywhere is Revit, and they are using, the ETABS is the most common in Middle East. So actually, it is not fully connected. I mean, you cannot simply I just made one change, automatically it will change the Revit structure. I think there are manual input is required as well. I'm not sure in 2019. I'm talking about up to 2018.
Yes, even for Revit now we have 2020 version now, and even ETABS and SAP have provided their latest CSI extensions too. If you talk about the connectivity of from information point of view, like with IFC, so that is 100%. If you talk about doing it manually by clicking that and CLAD.
I'm not talking about, for example, I started the project. The architecture and everything, this, initially the architect will make a design.
Okay, yeah.
So now, say this case story building,
Yes.
now the structural
model,
gives the picture.
Yes.
So what they will do, they will model the things, I mean. So
No. The same Revit architectural model is converted into a structural model in Revit, and then that is through CSI extension. It opens up as it is in as a structural model in ETABS or SAP 2000, and then you do the typical analysis and then reinforcement overrides and all these things, whatever you want to do. If it is RCC or if it is steel, then you will all that goes connection details and everything fixed and all whatever. And once that is done, it is the same model with extra information of reinforcement, or if it is steel, then the bolts and then the number of bolts and the spacing or weld and the length of the weld and all these things will come from SAP or ETABS into Revit, and then the things that we don't see in SAP and ETABS, the positioning and then proper detailing of that bolt connected and then all these number of threads and everything will be then shown clearly in Revit. Not required to be done manually in that. It is done automatically. But that effort is manual, you're right, to click and send it to SAP, and then that is fine. But then the thing is, information is completely transferred through IFC. IFC, through IFC, it is 100%.
100% or it is 80%. Because from my experience, it shouldn't be, transfer is there, but it's not 100%.
What is missing?
For example, whatever model you are getting from Revit to SAP, you cannot 100% utilize that one. You have to do 20 or 30% manual work to make it suitable to run your model as a structural model.
That's right. If you in Revit, if you only do the architectural model and then export that to SAP, then this is definitely the trouble you're getting in. But if you first create a structural model in Revit and then export it, it will be as it is 100%. Even with the loads, you can apply loads even in Revit and then it will be exported. But I don't think anything. There are few things like in slabs. You're right. The specific type of slabs with decking and all these things, they will not get modeled there because SAP has not the capability to model that. And it can do that layering and all these things in layers, but not with that deck shape directly. You have to do that through CSI detailing and all these things. Yes, you have to do that part manually. I agree with you on that part. Yes.
Yeah, also the reinforcement scheduling. I think that is also you have to do kind of manually.
Well, now
if you Excel sheet, then that can be exported to Revit. But Revit itself, I think, doesn't make the, for example, column reinforcement scheduling. How many reinforcement you need, outer column, then side floor, top floor. I think still you have to do it manually in the Excel.
For certain locations, yes, there is some. Let me call that as an engineer's feedback on the SAP results or whatever, you have to give some engineered feedback. I agree to you that in that form. Yes, you're right.
I'm just asking whether this that helps us. I
Well,
use that on your model.
Most of it is automated.
Now,
Like if you're using Bentley softwares, they
step or
it's not, the BIM softwares for Bentley. They have BIM, massive BIM, not only for buildings but also for infrastructure and everything.
microstation, that one?
Microstation was just a CAD tool for them, but now they call it open design tool.
I didn't know that one.
Yes, that is open design they call it. The best one now is by 3D Experience. This DS Simula, if you know, the Abacus software they developed that. Yes, their tools were actually developed for like manufacturing of complex structures like BMW cars and things like that. There's so much complex details. They converted that into building industry as well. It is very, very sophisticated. Very sophisticated. And
How
they,
about the training then? Because you are making the framework. But how do you, as the owner, how do you know that people are trained to actually interpret the results?
this is a very important question. For every um, for every office environment where BIM is going to be used, there is need to be a limited set of software that you have to select, and then limited level of D as well, that it will work up to 5D and 6D and so on. You will not work on everything, you will not do energy design perhaps or something like that. So you will select that, and accordingly you will purchase software and hardware for that. Because sometimes if you say we'll do everything, then you will also purchase Google glasses for the site supervision and all these things. It's going to be very expensive then. So let it be done by the contractor then. But the thing is, if you are following BIM and the contractor is also following BIM, then you are collaborating and connected in separate offices. So you yourself doesn't need any. There is no fixed solution that you do that. You have to decide your own. Like this is the limited thing that we're going to provide, but as per BIM on FC standards. So that will be then connected with any other person using BIM for different purposes. You will be well connected.
For example, if I do take a contractors, okay, I'm the owner, I'm the with the hospital. So how do I choose a contractor? How do I know that how is the ranking there in terms of pay? Then it's standard ranking.
There is a owner's manual for BIM implementation. So the owner will read that first, and they will know that if I'm going to take a contractor or a consultant, they should be able to do all these in the contract. So if they are not doing it, they are not following BIM.
It is not other way around. That there's an organization like there's a ranking. Okay, this contractor has that much ranking, so there is another. Okay, they're very good at that.
There is a certification by Building Smart for individuals and companies as well. They rank them. Yes, you're right. You can get golden or platinum or something like that from a certification from them. You do this.
LED certification.
Like lead, yes, absolutely. Then that is for the buildings. This is for the accreditation purpose. Like your office can provide that level of BIM.
Yeah, that is safe.
Yes, yes, you can do that.
Which one is the popular? I mean, Revit,
Yes, they are using Revit as well. Yes. Mostly around the world, Revit it has developed quite a lot. But then the type of solution that 3D Experience give in BIM, which is phenomenal, really. So because this has already been implemented to BMW and things like this, so it is a strange type of details they have. They literally their software connect to satellite to get a fresh image of the site. Satellite data they even take.
Yeah.
Today is it possible?
Today, yeah.
Okay.
We can do that after Saqib's
Okay, great.
presentation. We can go and visit the lab.
What's that?
After you're done,
Yeah.
then we can go and check the lab.
Yeah, that would be great.
I'd like to see the equipment you use in your system, your green.
Yeah. Yeah, like we also have some off-campus.
There's this place called Bike Shop Cafe in Cairo. It's right downtown. So I'll send a responder to you.
But whatever we
Send it to
have,
Andrew and Raj. We'll post it there.
Awesome.
I'll ask Sherry.
I assumed you're
We
viewing
speak
the
that up.
stream tomorrow.
Thank you.
No,
Or
we have
Wednesday?
on Wednesday we have another
Yeah.
meeting with another consultant.
Oh,
A
okay.
YouTube video of your interview.
Yeah,
There
that's
was
a
in the background,
nice
there
convenient location.
is
Yeah.
testing
Okay,
purpose.
yeah, there we go.
Your cylinders, I don't know what was to be tested,
That's,
but there was
Gather the herd. Gather the herd.
jack or something like that. But that was hammering on the cylinder. It
Shoot
was
them
a slow hammer. Not fast, it was actually going down and up and down.
Yeah.
Very fast actually. It wasn't slow. Do you recall that?
We do testing do strain rate effect tests.
Oh, that is the that.
Yeah.
I
So,
see.
yeah, you can control the rate.
Okay. So that is a typical.
But-
You didn't use the
6
machine?
hours
Yeah,
more
yeah,
They
today.
just use that.
Yeah. And also
This
we
one,
do also impact
we'll
tests.
see. That's
And also we have.
I'm not gonna belabor the numbers
off-campus
too much,
session,
but
we have
there are a few numbers
a
here.
shock test, but that is acceleration driven.
I know. So what I
It's
have
kind
is
of
our separate
simulate
PDFs for
blast.
people to look
I
at
see.
that I'll give to him to upload. You can read. Yeah.
Shock wave comes.
While
Yeah.
I'm presenting, I'm just going to talk about it. So just listen to me. Yeah, it's not the numbers. It's just the ideas that I want to
So
talk about.
you.
The numbers I'll give a
also
separate
what is your
PDF, which is
research
a lot more
project?
readable. Yeah.
Materials.
So when you want to
Currently,
run
I'm
through the
working
numbers,
on
you can have that. Yeah.
Specifically mud. Because there's so many chemicals in the market that they have discovered but never been used. It's very recent discoveries of them. So I just started to pick the gluing
all
one
of you
and all
design,
those and
I mean,
try
we have
so many
20
of
years
them.
experience.
We have discovered few which are the nerd
Anything
and
that you started with hand
I try to
very
do that.
concept,
Yes.
how
I try to
and
do
then
that. I try to dissuade people from
work done
just
in Brandon.
getting into a computer
They
and
have
and then running a non-linear
statically
time history
just,
analysis right away.
connected
You gotta understand things and
static forces.
but, go from the basic to more complex.
Literally,
Yeah.
So, I mean,
it's a very
how many
strategy
non-linear
there.
time history analysis you have to do?
That was very
Take some
interesting.
decision, or
I'm
basically
going
you
to try
more or less
that.
rely on the
It's mainly about finding
We've had to do lots of pushovers.
Because it is then
Lots of
usable and
pushovers.
reusable.
Yeah.
non-linear time
Non-linear
My
time
PhD
history
was in
a few
Saqib
times,
comics,
not
which
a
is,
whole lot.
EPS form with steel mesh.
When you get into big bridges, then you
Put it
need
to the
to
side,
run those.
erect it all
Then it
the way
becomes
to
mandatory.
20 stories if you want, and then short treat it in all sides. So
So
the whole building
It's
becomes
the
single
most,
piece.
yeah.
With all the
If
things connected.
people can do that, that gets you a
There are
long way.
multiple load paths, so cracking and energy distribution, so many things, so many problems are solved. So
I
I did
wasn't
that
part
in
of that.
complete, but then I'm also this
That was
mud
TYLN and
in
IBT, both
we
American
have achieved some
consultants.
good results.
On the big
Now we
bridge.
actually can
I wasn't with McElhaney at that point, and McElhaney did a lot of construction engineering for the for a lot of the highway bridges that cross
building
the
this
highway.
comparing with
I was with MMM at the
we
time,
started
and I somehow just completely missed that whole Portland Highway one widening. I was working on other stuff. Just
I developed software as well.
so, are you a UBC graduate from?
Even hardware is
Oh, to Western. Okay. Oh, yeah.
in Houston, one of my main projects was
Oh, is that right? So back when he was there,
Camera
doing his
based,
PhD. Okay.
intelligent artificial intelligence detector, which detects the
Okay.
movement of the
I
person
know
walking in front
Katsu
of it.
Goda is
So
there now.
from
He's
their
a
gate, it will
Japanese
judge
guy
that
who's
they
come from
really
Bristol.
intend to enter the door or
And he's
not.
part of my
So
community.
if they,
He's a very
they
probability.
want to enter, they have a special way of walking.
Yeah.
So detect that and open the door only for them who are detected to actually enter. And it works perfectly.
Okay.
So I developed that hardware and wrote the
We had
software.
some
So
French people there.
I just have my hand
Oh,
routine.
that's
So many things. So whatever I think that is useful and it can be done, so I just do.
Yeah.
Sure.
Should we get the people, or have they
Yes.
just? I mean, I see the books around, the notebooks around.
Huh? People are not listening to you? No? Did you text?
I'm just saying people know they should be back, so if they want to.
Okay, let's see. Who is more effective? Text. Okay. Farooq is calling.
One second.
Oh.
Oh, he's a
Mariam, text it.
We can just text Sherry.
Yeah, text Sherry.
Yeah, yes.
Okay.
Text. And just mention
Who?
Arman Harris.
Oh, okay. I know that Arman has to go after an hour.
No, Arman needs MS.
Oh, Arman.
Where is that other fellow? What's his name? Rahim Zadeh? The guy with the hair? I remember.
Oh,
It makes me
Rahim
very
Zadeh.
jealous. I used to have hair like that.
Oh, yeah. Ahmad. Yeah, Ahmad.
Yeah, he's not here.
He has a PhD comprehensive on Friday.
Oh, okay.
So he's a bit
He's obviously busy. Yeah. He's deep
studying,
into it.
busy studying.
So is he doing the written one? Yeah. So Chi was one of the last ones, I think, with the oral.
Oral.
Or is he?
He's the last one.
He's the last one. Okay.
Ahmad, because he's been here for 3 years.
Oh, okay.
Almost finishing his third year in,
Okay.
yeah, it is August. So
Okay.
the rule is you have to complete your comprehensive
Before 3 years. Yeah.
before 2 years. But
Okay.
somehow, Carlos was in the team
Okay. So that's
and
not.
it got delayed,
Just got
delayed, and finally we cannot pass beyond 3 years. Then
Right.
it's very so.
So is Carlos not part of the team now?
No, he is.
He is, but you've kind of arm wrestled him. Okay.
Yeah.
He already knows I'm doing it in January.
Yeah. I think maybe we have to send another reminder.
Yeah, I think we should send another reminder.
The good thing is he will send questions,
Yeah.
so it's easier.
Right.
Yeah.
Oh, whereas for this one, he has to come physically.
No, not physically.
Because it's oral.
Like he has
But
to attend for
he has
3
to
years,
sit for.
3 hours.
Yeah. That's hard.
Yeah. So yours hopefully.
Mine hopefully
Will be
is.
easy.
I'll just face some tough questions, but
Yeah. Long question.
long questions. Okay. Not making me feel good.
Yeah, it will be long. Like I received questions for Mariam, so I checked. These are long questions. It's good.
He thinks you should spend all 7 days on his questions. No,
No, mine will be easy.
no, not yours. He thinks
Oh.
you should spend all 7 days.
Yeah. Oh yeah.
Exactly.
Yeah.
Everyone.
One even asked her that she should spend 3 weeks
Who asked? Who
on
said
this
that?
question. Dr. Milani, is he part of your group? Dr. Abbas Milani?
No.
He's a final in time.
Okay. Now I'm scared.
It's okay. So, where do you?
It's two, but then actually.
Okay, let's give it maybe 3-4 minutes, and then
Yeah.
I'm gonna start at 1:55
Yeah.
because we're gonna keep going. Then it's just
Yeah.
gonna get too delayed. Because I want to at least get to the pushover part today. Otherwise, we'll have too much tomorrow.
through the description and see what this part is covering. Because sometimes you need the whiteboard. Now it's like if you see the sorry, that's showing
I should have been giving a time.
Okay, I think let's start. Otherwise, we'll be here till 7 o'clock. So let's talk a little bit about modeling. And the one thing I want to talk about is the deck modeling for seismic analysis. So I'll draw a typical cross-section of a simple girder bridge. Okay, so it looks something like that with your girders, and there may be a bit of a haunch here. You can think of these as, say, steel girders for this case, and a reinforced concrete deck. Now, a lot of people would do a full-on finite element analysis or finite element discretization of this and put that in their model, which, if you think about this, and if we say that reasonably speaking, this is going to act as a rigid diaphragm, there is no need to do that. There is just need to capture the overall mass, the overall vertical and transverse stiffnesses, and the appropriate area for this. And if your bridge is, say, multiple spans, say 2 spans, just to keep it simple, you can model the deck with a stick. Okay, so you can model the one bent, and let's say that longitudinally your abutment is free. You should really just be working with beam elements. There is no need to have this as shell elements and brick elements and all that. That's not the intent, right? Because seismically, we've already discussed, your load is into this bend. That's the critical element, not the deck. However, the load is generated due to the deck. It's the mass of the deck and the CG of the deck plus the stiffness of the deck that drive the generation of the seismic load. The resistance comes from this. So what we want to do is we want to have a beam element that kind of goes from one side to the other and maybe discretized depending on if your girders are changing sizes or whatever. Nevertheless, we want to just capture it in one spine. We call it a spine model. When the bridges get really large, then you can start to lose some of the rotational inertia effects, and then you might want to think about having a grillage, which is, you know, multiple spines, and so you could run a stick at each one of these girder locations and have some transverse elements to model the deck. Whatever it is, reasonably of reasonable width, not too wide. If its aspect ratio is not too, then you can really just do this. So what I want to talk about is how do we come up with the vertical stiffness of this, the transverse stiffness of this, the area, and then the CG. The CG helps us come up with the height of that element, which puts the CG of the deck at the right location. Because imagine if your load is being generated here, it has a certain lever arm to your foundations. If it's generated higher, then if you model it lower, you're going to have a bit of a discrepancy. You're not going to be able to capture it appropriately. So I've got a little example which is hard to read, but I'm going to give you a separate PDFs to go through the numbers. But this basically, all I want to talk about here is a simple idea of the transform section. We all know this this N, which is ES over EC, going back to again, reinforced concrete 1. So if you have a concrete deck and a steel girders underneath, we want to do something to this thing to come up with a composite stiffness, overall stiffness. And in this case, your girder dimensions are going to let you come up with the vertical and horizontal stiffness of each girder. And each girder has a certain area. So all that is in terms of steel, because that's a steel section. What we're going to do is we're going to transform the deck into an equivalent steel section so that everything is now working as steel, just in terms of capturing the stiffness and the weight and all of that. So we calculate our modular ratio, which is N. Now, when you're looking at the vertical stiffness, you only want to change the width for the equivalent section, because if you change the depth, then you're artificially changing the CG of your system. So when you're looking at your vertical distances or vertical stiffnesses, you're reducing the width of the deck. When you're looking at your transverse section, now you're looking at reducing the thickness. So for vertical, you have this total width, which is 10.98 meters, and you divide it by 7.4, so your equivalent is only a slab, which is 1484 thick, with the same depth of 225, but now it's steel. For horizontal, you're reducing the vertical, right? Because that doesn't impact this way. It's this width that's going to impact. So now you divide the 225 by 7.4, and now this is a deck which is 10.98 wide, but only 30 mils thick. So using those numbers, you have your transformed sections. You can come up with the composite Y, which is the distance to the centroid of the composite system. So that's 2215, which means if this is, say, 3 meters or whatever, your CG, your composite CG is a smaller number. And so then you can build this model and you can come up with the height of that stick based on that distance and whatever else is going down. So you can go through this, but this is again just calculating like the centroid of a section. There's nothing else to it. It's just got 4 girders and a plate sitting on top, which is steel, both vertically and transversely.
And what are the properties of this vertical stick?
So those are the properties we're trying to calculate.
Yes, that is for the horizontal one, but the vertical stick. Yeah.
Oh, the vertical stick is just a rigid element. Because really this, when you're making this sit on top of a cap beam, you have this artificial stick that takes you to the CG of the deck. So what you're doing is you're just putting a rigid offset here to capture the appropriate CG, the center of gravity of the system.
So if the span on the left and the right side are different,
yeah,
then don't we need any for the torsional effect on the cap beam?
Yeah.
Will that still the rigid element be okay?
Yeah, it's a rigid element that you can use. It's fine because the stiffness will come into this beam itself. So you've got to capture the appropriate torsional stiffness of the cap beam.
So it is also transferring the torque in the cap beam?
It's only going to transfer that because
Vertical
of this horizontal load and this eccentricity.
The moment.
Yeah.
The torque. That
becomes torsion into your cap. Yeah. But you will see that torsionally you need to crack. You use crack stiffness of the cap beam and really drops it's quite low. Once it cracks, you're not even 25%. And so in reality, there is very little torsion in these cap beams because they crack very early on. Reinforced concrete cracks very early on, especially in torsion. Okay, so this is just doing some math. You've got the 4 girders, and then you've got the 4 AY squareds, and then the deck and the AY squared of the deck. That's all it's doing both ways. And I'm not going to say much more than that. You can come up with the numbers quite easily. So I talked about this a little bit earlier, where you have to have the effective stiffness. And Dr. Priestley produced some charts that I want to share with you. You might have already seen these. instead of doing a moment curvature analysis where you come up with your effective stiffness based on the line from the origin to first yield, you can, when you're starting off and you don't have a real clue, you can have a column like size based on just gravity loading. So what am I going to use for my seismic analysis? If you're not using a refined moment curvature analysis in the beginning, you're doing some conceptual study, or you're just trying to size them up, you can come into this graph. You know what your P is, your axial load, over F prime CAG, that's the axial load ratio. So you divide by F prime C multiplied by AG. That's all in the denominator here. And you see how much rebar you're going to put in it. So maybe for non-seismic reasons, you're going to put 1% rebar. And if your axial load ratio is, say, 0.15, you come up and it's a circular column. You read off of this and you say, my starting stiffness is about 0.35 Gs. So you use that to run your first analysis, your first iteration. Once you've honed in on the solution mostly, then you can go use a moment curvature analysis and verify it. But these have been done after extensive studies, so you won't be far off. You won't be off by that much. And you can see the range. If you have 4% rebar, which if you stuff that much in there, the contractor is not going to be happy. And your axial load ratios, you may get up to 0.7, and you may get as low as about 0.3. That's sort of the range we're talking about. I will tell you that good design for bridge columns is 1 to 2%. 2.5%, now you're starting to push the system in terms of rebar congestion and being able to vibrate it, and that's just starting to push it a little bit. So at that point, you might want to look at a slightly larger column. Don't oversize it too much. And you want your system under gravity load. If you're starting, you want it around 0.1 to 0.15. That's where you want to be. So if you know how much is coming onto a given pier, to come up with the number of columns, you should probably target about 10 to 15% of the axial load ratio. That will give you a good number of columns for a given size that you can decide. And then try to stay within 1 to 2% rebar. Remember that the code bounds are 0.8% minimum and 4% maximum. But 4% rebar is really huge. And if you have to lap splice it, then you're looking at 8%. You physically can't get 8% rebar anywhere. You won't be able to do much with it. Okay, so here's an example. It's a 1.8 meter diameter column, and it's got 2635 M bars. You calculate your AG and the area of the steel, so you get your P over F prime CAG. It's about 8%. Steel is 1%. You go into that graph for a circular section, and you see you end up at about 35 or 0.35, 35% effective EI. This is the second method now. We talked about the uniform load method. This is the second method, which is a single mode method. It has a bunch of integrals, alpha, beta, gamma. It's got an arbitrary load. I'll explain this in a quick minute here. And eventually you get your period. And from the period, you then have this expression that you can use to come up with your load intensity, just the way we came up with it early on for the uniform load method, to apply to your structure. Again, only to be used when your bridge is able to behave in the first mode, or is really just predominantly behaving in the first mode. I have here a derivation of this, which I won't go through, but really the idea is, again, the same. It's equating the potential energy to the kinetic energy. And so if you go through this, then all of a sudden the code integrals that are just thrown at you, they start to make sense. So if somebody's so inclined and you want to learn about this, you can go through this. I've done it in a very simple manner, and I say, okay, here is your potential energy. It's half times P times delta, and then that's where the integral comes from, and then maximum is that, so alpha is that. So it's all, the derivation is basically there. It's step by step, so you can easily get to the same formulae as they're presented in the code. And then when you look at the code, it's or when you look at modal analysis, your Vx, which is the maximum response, is given by a spectral displacement for unit mass and the mode shape ordinate, and then there's a modal participation factor. And that is dependent on how you normalize your mode shape. So there is a dependency there. So in this case, the mode shape factor is given by an expression which is a product of your mass and the mode shape. And once you go through that, you exactly arrive at what the code is doing. So if you look at some of these, you'll see I've put some physical meanings, like here's your mass and here is your mode shape. So I'm not going to go too much into this except for the fact that when you combine all of this, you come up with your Vx, which is your spectral acceleration divided by accelerate, or your frequency squared times the mode shape times these two factors. I have a spreadsheet that I will share with you guys. It's a simple Excel spreadsheet that I will have Sharif upload, and you'll see that each one of these steps is modeled in there, and it's just very, very simple to follow. So I don't want to spend too much time on this. I just wanted to bring this to you, that now this is the PE, the total load that you have to apply to your model. Okay, so here is again an example. I've got 3 girders plus some deck and some asphalt on top. I've got the total lengths, so these are different length spans. I've got the heights, etc. So all the data is there. I've given different weights for each section because as the bridge, to make sure that we utilize the material properly, we don't use the same girder sizes everywhere. We optimize them as best as possible. Okay, so that's just giving you a lot of the information as to what the bridge looks like. This is the pier. There is a section 3, which is either side of the pier. At the pier locations, you tend to see a lot of negative bending moments, so the sections get heavier. Then in the mid-span, you see more positive moment. The sections are a little bit lighter, but now your bottom flanges are thick, the top flanges are thinner. And then section 1 see minimal, so now you have another opportunity to skinning up your sections because you don't want to use material where it's not required. So based on that, you can come up with the deck weight and the weight of the section 1, and then come up with an equivalent steel area. Same thing with section 2 and section 3. And this is where I'll spend a little bit of time. How do you model this? Again, you model it with stick elements. You can model 3 or 4 elements. Then you have rigid sticks that take you to the CG of the cap beam. So all these elements are pretty much rigid elements. So that is ignoring any flexibility in your joint. You should be mindful of that. If you want to take that extra bit of, how should I say it, refinement, then you need to model some sort of a rotational spring. There is usually no need to do that if your joint, because your joint afterwards is going to be detailed properly to make sure that it does not soften up. So that's the whole idea, that you're going to design it so that it doesn't crack badly and it has enough strength and stiffness to not turn into a pin. It stays as a moment connection, and then you don't need to. And you can do that in a new bridge because you're controlling this thing. Then you have this rigid stick that takes you from the CG of the cap to the top of the cap, and from there to the CG of the deck stick. So these are going to be rigid elements. Okay, so let me just pull up this spreadsheet very quickly here. I'm not sure why this is. Okay, let's just keep it like this. So what I've done is I've taken a lot of sections through my bridge, and I've basically, my spectral acceleration is 0.8. I've just assumed that for just elaborating this thing. And now my P naught, which is that initial load to get my stiffness, is 10 kilonewton per meters. Okay, so I have my west abutment is location 0, and then I divide it up into a lot of segments. I know what section I have at each one of those mid sections, the length of it, the weight of it. Then I multiply Wx with dx, so that's just being multiplied to get the weight. I get Vsx, which is given here based on the formula, Vsx dx, Wx Vsx dx, and then the squared of that, and then out comes this Pe. So what you're seeing here is the transverse analysis, the load is not uniform. The load is only uniform per section. So the more you discretize it, the better results you're going to get. So then you go into your model and you apply these loads. And when you see up here, you will see that these are pretty simple. These are pretty simple formulas that you can just multiply around. And what I wanted to show you here is I've got the total weight, and alpha, beta, gammas are all calculated here. From this simplified analysis, I got a period of 0.3987. And when I just do everything in CSI bridge, I got 0.406. So they're very, very close. Right? They're very, very close. This is transverse, and then you go to longitudinal. And you basically repeat the same thing, it's just in the longitudinal direction. And again, you see that you've got some differences coming through. And here you see a little bit of a different scenario. You see this method is producing 0.73, and CSI bridge is producing 0.83. So there is a little bit of a difference. Can somebody think of why that might be? So look at
How did you apply the mass each location?
now the mass is the mass is assigned to each element.
Is it the horizontal mass or it is not in both directions?
It's once you apply it, it acts in both directions, right?
Both directions.
Yeah.
Okay.
Well, if you apply it in CSI Bridge or any other software, it applies it vertically, horizontally, and longitudinally and transversely.
So two direction mass each location.
Yeah, it's just each location is that. So if you look at this, I've got longitudinal vertical rigid deck. So in the previous case, I wasn't. So in this case, I'm assuming my deck to be very rigid in terms of the area. So the mode shape, and I'll show you in a second. I think let's just show you on the graph, but your mode shape is like this. Okay, and that's when you get a very good comparison between CSI bridge and this method. Whereas in reality, when you have a finite stiffness, your deck tends to curve up. And it gives you a longer period, and that's where they don't match very well. So here, you're not getting a very good match. Okay, so if I show you, now let's go back here. So this is a single mode method, 3D model. This is just after this is a longitudinal displacement profile, and you can't really see very clearly, but the column is, the bend is doing this, it's bending forward, because I've applied 10 kilonewton per meters of loading this way. Why is it stuck? Oh, I think I have to go to this. Okay, this is the transverse profile. So you see here, and you look at this, and then you look at this. This is where the deck, the actual axial rigidity is modeled appropriately. So you see this hump in your mode shape. Whereas when it's very stiff, you you see that it pretty much stays very, very straight. Okay, so the method, the simplified method doesn't capture that. This method does. The simplified method just assumes it's a rigid stick because it doesn't have any way of figuring out what the local flexibility of the deck is. So when you put an infinitely stiff stick in SAP, if you bump up the area by a factor of 1,000, all of a sudden the two match very nicely. But you know that that's not correct, and that's what I mean by keeping your mind open. So SAP is giving you the right behavior here because you've got the actual area that it accounts for within its finite element formulation, whereas the single mode method doesn't do that. Yeah. So this is just showing you the longitudinal mode. It's amazing that this is still working. And you can see here, your columns are going into double curvature, right? You can see that the double curvature on the columns. In this case, you see they're fixed at the bottom, but there is nothing to force. Because these 2 points are free to go, they're working as a cantilever. So they're going in single curvature, and hence the 3 EI over L cubed stiffness versus the 12 EI over L cubed stiffness. So now this is the rigid deck animation. Now you can see how the deck is staying pretty straight. So this is a stiffer system. That's why its period is 0.5 something instead of 0.8 something, because the deck is not accounted for. These are the sort of things I would like everyone to think about. This is another idealization. You can, just to come up with the same thing, you can assume your deck to deflect in a sinusoidal shape, and then you can go through this. And at the end of the day, you come up with very, very similar results. But with that sort of simplification, you can just come up with something that's like this. So you don't have to go through the code formulas. You can use this and it'll still put you pretty close. I would just, if you're ever using this, I would just use the code formulas. Now, here's the thing. Here's my personal thought about it. You still need to have a bit of a model set up, right? To apply that initial 1 kilonewton per meter or 10 kilonewton per meter load to get your basic deflections, to get your stiffness. By the time you've done that, you've basically made all the effort. Let the program do the work after that and come up with the mode shape. The things you should be looking for are the following. To check that you haven't made a mistake in your input and that the software isn't doing something kooky. Have a look at your total bridge deck mass. Run your gravity analysis in your model. Check that the total reactions are equal to the total deck mass plus whatever little bit the columns have. That should always be your first check. Have I accounted for all the dead load? Okay. Check very simply with the 12 EI over L cubed or 3 EI over L cubed what my period should be in that sort of range. It won't be exact, but if you end up within 10-15% of what the software is giving you, then you know that you're close enough, right? You haven't missed a fundamental thing in terms of stiffness and mass. Those are the two things. So do those little checks, and then once you've satisfied yourself that your numbers are making sense, then you can rely on the software. Just don't rely on it blindly. But I also don't want to say these are useless methods. I also don't want to overemphasize their importance, because you have to do the work to set up that model, to come up with, unless it's just so simple that you can just come up, like the uniform load method, I think is probably better, where, if you can just come up with a 3i over L cubed type formulation, you get the stiffness right away, you get the period, carry on. But then you should have some idea of, okay, if my bridge is this long, it's this heavy, is the period going to be 0.7 seconds, or is it going to be 3 seconds. Don't miss the mark on the big things. Okay? So here is a comparison. I've done a comparison with the solved example based on this sinusoidal mode idealization, and you can see here with these expressions that I've given you here, with the period and everything, I get 0.384. The spreadsheet is 0.398, and CSI bridge is 0.406. So 0.38, 0.39, 0.4. Very, very close from the 3 methods. And my effective load, the maximum loading intensity, because it's changing, so I just compared the maximum. I got about 134 kilonewtons per meters versus 137 kilonewtons per meters, which is based on the core methodology. So again, you can see that there is a fairly good match there. Okay, so this just goes on to talk about how that sinusoidal idealization was prepared, or how we came up with that. Okay, so let's move on to multiple modes now. I think we've kind of done enough for single modes and what it needs. Now the extension to multiple modes is rather natural. Okay? So the idea is that each structure vibrates when it has multiple degrees of freedoms. Its vibration is a combination of different modes. Okay? So if I have a 2 degree of freedom system, it has the first mode like that, it has the second mode like that. A lot of the times I'm asked this question, people run the modal analysis and they draw the mode shape, and the program gives them displacement values of there's a displacement there, there's a displacement there for first mode, and it's 1,024 millimeters, and the young engineers come running to me and go like, wow, my modal shape is it just doesn't make sense. And I say, I'm really glad that you picked on it, because the mode shape is nothing but a ratio of these numbers. That's it. It's not an actual displacement value. It's just telling you how much 1 degree of freedom is moving relative to the other degree of freedom. So this could be 1 and this could be 1.3, or this could be 1,000, that would be 1,300. That's it. It's just normalized in a certain way. It's not the actual deformation. It's just a vector that defines the relative, the ratios. Okay? Same thing here. It's all ratios. It's not until you run the response spectrum that you start to get actual displacements. Until that point, these are just ratios. So we've seen this equation before. Now the M and the C, the K, the U's, the U dots and double dots and P's, they all become matrices. And that's why there is an underline in there. Now here's the whole thing. Any set of vectors, a set of vector of independent vectors can be used. Let me rephrase, let me re-say that. Any set of independent vectors can be used to arrive at a different vector. So these vectors that you use to arrive at the final vector have to be independent. And by vector independence, we mean you can't just, they're orthogonal. Okay, so as long as your vectors are orthogonal, you can use them, they're independent, i.e. one is not just a multiplicative, one is not just a multiplication of another one, so it's not like one is A and the other one is 3A, because that's the same vector. They're not independent, they're linearly dependent. If they're linearly independent, you can have any set of vectors, add them together, and you can get the final set of vectors. That's what underlies this whole thing. Okay, so we say our final displacement is the deflected shape times some time varying quantity. And that time varying quantity is captured by this Q. The phi is the mode shape. And now these are vectors because you have multiple degrees of freedom. This is not just one displacement, it's many of them. And when you go through the mathematics of it, you find that after you've applied modal orthogonality, where because the modes are orthogonal, mode number n doesn't do any work in going through mode number r, that those terms are zero, they cancel out. And at the end of it, what you're left with is decoupling of modes. So for each mode, you get one equation. So now your overall multi-degree of freedom system is has been decomposed into independent sets of single degree of freedom systems with different periods. So now this equation is applicable to a particular mode. And this is again a matrix equation, so M is a diagonal matrix. So because that's been diagonalized, it's one equation, one equation, one equation. They're not simultaneous. You don't have to solve them together. They're all independent. So each equation can be solved independently. And guess what? We've solved one equation before, which is a single degree of freedom system. So now this multiple degree of freedom system has been decomposed into many, many single degree of freedom systems. And you solve them separately, just like we solved the first one. And then you combine them, as I talked about, with directional combination, and then with the modal combination and the directional combination. So this is giving you the equivalent equation of motion for one a single degree of freedom system. So this is one of the many that you've decomposed the system into. The advantage is that these equations of motions have been decoupled from each other. So there is no reason to solve them together, no need to solve them together. They are in their own coordinates. Yes, sir. Yes.
This, you said this equation number
F?
Yeah,
This one?
F1, yeah.
Yeah.
This A is diagonal matrix, okay.
Yeah.
But C and K,
They are all diagonal matrices. I should have mentioned that. So this is for true for classical damping. C becomes a diagonal matrix. When it's not classical, then you cannot use the classical response spectrum analysis. Okay, and the same thing with the K. They all get, because what happens is when you have the phi n, so you see this K, that's equal to 0, right? So that's any off-diagonal terms are 0 for both mass and the K, and the same thing happens with the C.
this K is the original K or is the modified K somehow? Is the original stiffness?
No, this K is going to be different. It's going to be capturing the equivalent stiffness for each one of those single degree of freedom systems. Because the original K is just a large matrix. This will be one number.
Okay, I thought there's a
Yes, no, that's a good question. That's not the original. The original is a large matrix, right? Because we have a multiple degree of freedom system. So this will be a diagonal matrix of K values. Every off-diagonal term is going to be 0. And now that K is only applicable to that particular single degree of freedom system. And that's how each equation becomes different. This P is also, originally it was a matrix of loads. Now it decomposes into a vector where the P is only applicable to one mode. So as you go down the rows, everything is independent, it's just assembled in a matrix. So to get the, this is now in modal coordinates. This is not in use, okay? Now you've decoupled it, but now you're working in a transformed system. You're working in the modal coordinate system. And so what you need to do is, again, you need to solve that equation of motion, but it's a single degree of freedom system. So you can solve it whether you use time history analysis or you use a response spectrum, whatever, you can solve that separately. And once you've solved the Qn, which is in the modal coordinates, you multiply it with the mode shape to get the actual displacement. This is now bringing it back to the original coordinate system. You transform them to the modal coordinates, now you're bringing them back to the physical coordinates. Okay? So this U and T is basically at a given degree of freedom for a particular mode. And now to get the same thing from all the modes, you have to combine these together. Yes, you have to combine them. If you're running a time history analysis, you can do this by not integrating the equation of motion. You can go through this modal route as long as it's linear, because modal is a linear. You can use linear superposition because everything is basically elastic. You can do that, and then you're only solving in time history. You're solving single degree of freedom equations that are decoupled, and at each time instant, you're calculating the actual response for that mode, for that degree of freedom. Now you can add them together for the same time point. That's 1 plus 1. But when you go to the response spectrum, you can't do that because those are maximum quantities. Okay, so that's what this is doing. Now you can add them all together over all the modes, you sum them, and you get the displacement. Going back to the original equation for force, that's displacement times the stiffness, and out comes the force when you sum it all together. Then you can apply that force up and down your system, and you'll get the internal forces. Okay, so I think a bit of this is already covered. It's just written in a better manner here. And this is going through the formulation a little bit better. It's basically showing that UT has been basically decomposed into the modal coordinate times the mode shape. And then the Qn, the time varying component, has a cosine and a sine. And you put it back in there. So in mathematics, it was a very nice idea. When you don't know, when you're really stuck. I heard this on a YouTube video and it stuck with me for about 2-3 years. And this guy was just amazing how he put it. I'm going to try my best. But basically he said, if you don't know the solution, you think of a solution and you put the solution into the problem. You force it, and then you see what parameters come out of it. And now with that solution and those parameters that come out of it, you've actually got the solution. So this is the same idea that I don't know what to do with this problem. I'm going to say, okay, my solution is of this form. That's how we solve differential equations. We say, I'm going to say my solution is e to the power of minus ax. And I'm going to put it into the differential equation, and I'm going to see what falls out of it. This is the same idea. I'm saying my displacement vector is a sum of something. It's got mode shapes and it's got time varying components. I'm going to take that, I'm going to put it into my differential equation, and I'm going to see what falls out of it. That's all. That's the jiggery pocketry that's happening here. Okay? So when we go through that, we come up with this equation number 6, and there's the k minus omega squared m term. Its absolute value has to be equal to 0. So there are trivial solutions here. If phi n is 0, that means there is no motion. So that's a useless solution for us. Obviously we're looking at a case where there has to be motion happening. A non-trivial solution, because this is homogeneous, is if the absolute value of that matrix is equal to 0. And when you solve that equation, it leads to a polynomial of order n in omega n squared, and the square of the n real roots. Okay? That equation 7 is the characteristic or frequency equation of the system. And we already looked at this, and we kind of came up with, for a single degree of freedom system, this was our equation, right? So it's pretty much the same, except for k minus omega n squared m. If I write it for a single degree of freedom system, I can write it as k minus omega n squared n equal to 0. The same thing. When you extend it to multiple modes, it just turns into a matrix whose determinant is equal to 0. And once you solve that, you're able to come up with the n natural frequencies, And with the n natural frequencies known, you can come up with your mode shapes. And again, the mode shapes are dependent on how you choose your first coordinate, for example. Okay, so those are equations that are over-determined. So you put one value and the others come out. So they're relative to each other. I can put a 1, or I can put 100, or I can put a 0.1. The others will come out as a ratio of the first value. So very quickly, here is a double-decker bridge. You don't see those very often. I showed you one that had fallen down and miserably failed, but for other reasons. Here, I'm assuming that you've got a mass of m and a mass of m. Oh, we have time. K1 and K2 are 12 VI over L cubed. Right? They're both fixed. The mass matrix is m. The stiffness matrix, when you work through it, it turns out to be 2K1 plus K2 minus 2K2 minus 2K2 2K2. You can put in the values of K1 and K2, so you get 48 and 24s for your different terms. And now again, this is just going through that K minus omega n squared determinant equal to 0. Sorry, I've been saying absolute value, but that's the determinant. And when you work through that, and I call this quantity A, just to simplify it, my life becomes easier. I come up with an A, which then has two values, A1 and A2. When I use A1, I get one frequency. When I use A2, I get another frequency. And that matches the fact that this is a 2 degree of freedom system, and it should have 2 natural frequencies. Okay, so here I can see this one is 3.028. I've kept it in general terms, EI over ML cubed. So whatever EI you have, whatever M you have, whatever L you have, you got these radians per second. Now, mode 1, we go back to this equation, which is what we had arrived at earlier. We put the K and the phis and the omegas back in. So now I'm working first with omega 1. So when I put in omega 1, and I expand this equation, I come up with something like this. And my phi 1 comes out to be 0.618. Okay? And you can figure out your, so here, okay, sorry, that's what I was looking for. I've got this together. I can't solve these in absolute terms. It's just not absolutely determinable. You can't determine them. So I say my phi 2,1 is 1, and because I'm only after ratios, now I have this as a known quantity, because when I work with this whole system, it turns into a single equation with 2 unknowns, right? So you just don't know. So you just assume the first value. You can assume phi 1,1 to be 1, and then phi 2,1 will come out to be something else. But it's still as applicable as this case. I just assume phi 2,1 to be 1, and then my phi 1 comes out to be, or phi 1,1 comes out to be 0.62. I do the same thing for mode number 2, except for now my omega 2 squared value is what I had calculated earlier, so it's different. And here are my mode shapes. This is the deformation at degree of freedom 1, phi 1, under mode 1. Degree of freedom 2, under mode 1. So this is 0.62, this is 1. That's the ratio. You can have this as 620, and this as 1,000. Same thing. This one here, minus 1.618 and 1. So this is now going in some reversed manner. So the first floor is being pushed this way, the top one is being pushed the other way. So the method is pretty, here's how I've summed it up. You determine your mass matrix, you determine your stiffness matrix, then you do your form your characteristic equation. You come up with your natural frequencies and periods. And once you've calculated those, then you can come up with your mode shapes. For each mode shape, you compute your peak response. Now, because you're not doing a time history analysis, you're calculating the peak response using a response spectrum. So for all those different time periods, you're coming up with the maximum responses for those periods. Now you have to combine them with appropriate modal combination rules, and then an appropriate directional combination. Okay, so when we do the earthquake response, we bring in a vector of unit values in there, because then that works. It's just this L is equal to 1. You can look at Chopra if you want to see a bit more detail of it. So instead of, so this is the case where you don't have a P, you've got this, ground acceleration. The only difference now for the participation factor is not phi and Tm. There is a 1 there, because these are matrices, so to multiply them to get a number, you need to have a vector of 1s. That's all it's there for. It's no rocket science. And when you have a little bit of time, if you go back to the single mode method, you can kind of see the gamma. It'll have this sort of form. So you can actually start to pick up on the pattern. It's just the single mode and the multiple mode, they start to correlate very well with each other. Okay, so for each mode, you can have your base shear for your effective modal mass, like I was describing. It just becomes it turns into many degrees of, or many systems of single degree of freedom. Now, in terms of the combination rules for modal combination, you can use SRSS, which is the square root of sum of squares. I should throw this away. Or you can use the CQC. I encourage people to use the CQC. So SRSS is good if your frequencies are well separated. Okay, so CQC pretty much works every time, given the problem we're trying to solve. It's still statistical, right? It's not time history where you're adding the responses at the same time interval. You're still looking at maxima. But this is the form of it, and I'm not going to go through this, but in these notes, you'll see an example that kind of shows you how to go through this whole thing. So it's the same bend, an IE of 0.45 Ig, EC value, and a spectral acceleration. There's your mass matrix, the K, the stiffness matrix, so that becomes that. Then there's your characteristic equation, right? All the things we've talked about. Just to simplify, I say lambda is omega squared. So you end up with this quadratic equation, because we know we're going to get 2 roots out of it, right? And then you get the lambdas that are the square of the omegas. You take the square root, you get the omegas, you get the t's, and then we calculated the mode shapes earlier, so they're right there. Now we calculate the modal participation factor, and now you see that this 1 helps you. The transpose times this times that, and it comes out to be 1.1708.
Excuse me?
Yes?
Yeah, this is the modal matrix, I think, is 5T. So you said that it doesn't have any physical meaning. So it is kind of normalized matrix.
Which one?
The phi or theta p.
Yeah, this phi?
Yeah, phi. Yeah,
Yes, so as long as you stay consistent with it, right?
What does consistent mean? I think.
So you can come up with those phis a different way,
Yeah.
okay? Your p's are going to look different, but when you do your final steps, you will get the same answer, because the ratios work themselves out. And you can go through the math and you'll see that it doesn't matter how you normalize those. It's just that if you assume that phi 1 to be 1, then phi 2 1 has to be calculated based on P11, that's what I mean by consistency. Okay, so as long as you've done that and you carry through with this procedure, your modal participation factor is dependent on this. It might come out to be different, but then your final answers are going to be the same. So it's just, there's this ratios, and then it comes out because of the period and everything, it comes out in the wash. Okay? This is your P2. So this is why. Now I can show you why. You see this, to get your displacement, you're multiplying this P1 with the Phi1. Okay, so when you change the Phi1, you get a different P1. You can keep changing those, you'll keep getting different combinations, but the P1 multiplied by Phi1 is going to be the same. And then there is SA over omega squared, which is constant. So you can come up with a phi however you want it. Your P will be different every time, but the multiplication will come out to be the same. Okay, so then you can get your maximum U1. So that's for each level, and similarly you can come up with your maximum U2 at each one of the levels. So now, if I were to use absolute values, I can just sum them up. This is for example, I've done this. You see how this bridge is primarily behaving in the first mode shape. Why do I say that? This is the displacement at the first degree of freedom due to first mode, maximum displacement, 61 mils. The maximum displacement due to the second mode is not even 4 mils. Same thing down below, 99 and 2 mils. So in this case, it's trivial. I mean, you can add them together by absolute summation, or you can add them with square root of sum of squares, or you can add them with CQC. They all give you very similar numbers. Now, if the 2 modes or 3 modes are contributing 30% each, all of a sudden it's going to be a different story. Okay, so this is, again, this kind of hopefully clears it up that if you're going primarily in one mode, higher mode effects are not there. So the combinations, the rules that you apply are not very important. Conversely, when it is behaving in multiple modes, just adding their maximum values together, knowing that they don't happen at the same time, is perhaps not very wise. So we need to revert back to some sort of statistical combinations, which is SRSS or CQC. Okay, I want to quickly talk about, this is not very clear, but doing it using a software. So you basically have to set up a modal load case, and you can have a number of modes defined. You always start from a zero stress state, so don't put any load on it. You're assuming that it's not loaded. All the mass is there, but it's not under a stressed case. You have to input your response spectrum. Here, one mistake I tend to make is, for example, in CSI Bridge, when I put these as 0.61, 0.54, those are just numbers. Okay, so those are unitless. So if I put it like this, when I go into the load combination, I have to specify 9.81 meters per second, a factor of 9.81 to tell the program it's this many meters per second squared. Some programs might just take this as percentage of G and you're fine. But all of a sudden, if you put this into the program and you see almost no load in your structure, you know that you've put in like 0.61 meters per second squared divided by 9.81 is not even 10% of G. Okay, so if your intention is that this is 0.6 G, you expect to see a fair bit of load in your system. Just make sure that you've set up your load case and your load combinations properly. So here you see how I do the 100%, 30%. I have got this modal combination as CQC. I know it's hard to read, that's why I'm reading it out to you. The modal combination is set as CQC. And here is where I'm adding them. So U2 is one direction, U1 is the other direction. U2, my factor is 9.81, which is 100% of the G. And U1, I'm taking 2.48 or something, which is 1/3. That's how I'm applying the 30% G in the other direction. That's one load combination. The other one will be the reverse of it. Okay? SAP also has, or CSI Bridge, asks you to tell it the mass source. Where is my seismic mass coming from? So it could come from just the deck. It could come from the elements. You might also have a lumped mass somewhere if something heavy is sitting somewhere, which you may not have modeled in the bent itself. So you can assign a load to a joint, and then in the mass source, you can actually say, take my members, take all the loads that I've applied, and turn all of those into seismic mass. Okay, and your program can do that. So keep those in mind. And this is where now my dead plus seismic combination is happening. And if you look at the code says you have to use 1.25 times the dead load plus your seismic. So the seismic is this response spectrum, which is 1 longitudinal plus 0.3 transverse with a factor of 1. And this is 1.25 in the dead load. You also have to use 0.8. So in the seismic combination, when you're doing dead plus seismic, either you apply the vertical response spectrum in your load, in your model. If you don't apply, the code says use 25% extra downwards and 0.8 to account for vertical excitation. So you're artificially making your dead load lower and higher to account for the vertical excitation.
And we can put the mass.
Yeah.
Or you will calculate the gravity load, or the dead load, or we consider some portion of live load.
So in our code, we're only looking at the dead load at this point. Yeah. When you're exciting the bridge, you're only looking at the dead load. It has some clause where it says, after your earthquake, account for your damage and make sure that it can take 50% of the live load on it. And when I get to the pushover, I'll talk about it a little bit. But when you're exciting to come up with your frequencies and your inertial loads, you're only looking at the dead load of the bridge itself, no vehicles on it.
So I calculate this period when the frequency only I will consider the dead load.
Yes, yes.
I'm sorry. So you're saying you're using the vertical model analysis as well? We don't have to do the 1.25?
Yes, then we don't.
It's just then
No.
plus the-
Yes, and then your load combination turns, then you're looking at 3 load combinations. 100%, 30%, 30%. Then you're looking at these 3 combinations. Okay? Plus, of course, then your dead is, and it's always plus minus. Now you don't have to put any 1.25 or 0.8 or anything like that. Okay, so this is the 0.8, same thing. I'll very quickly touch on this and then we'll take a quick break and we'll move on. I was talking about accounting for the abutment stiffness and strength in the system. And I think it's a wise thing to do, especially on short span bridges. You can lock your bridge between your abutments if it's 2 spans or 3 spans and the aspect ratio is if it's quite wide relative to its length. So think about there's a saying in structural engineering, I'll see who can complete it. Stiffness attracts load, right? The more stiff something is, the more load it's going to attract. So if I have very stiff abutments, here's my bridge. Let's look at two cases. And infinity doesn't mean anything, it just means it's a lot more stiff than these springs. Okay? Now this is a relatively thin structure. If I push on it, there is a pretty good chance that it's going to deflect like this. Right? What does that mean? That means my springs have to deflect that far. Right? So if there is stiffness or if there is deflection in a spring, if there is deflection in a spring and it has a certain stiffness, what does that mean? There is force in that spring. Okay, so these are your piers. Even if my abutments are very, very stiff, but my deck is very slender, the deck is not going to act as a rigid diaphragm. It's going to bend itself. And when it bends, it's going to drag the columns with it. The columns have deformation, which then turns into moments and shear forces. Now let's think of a second case. This is still sort of very high, at least relative to this. How is this thing going to bend? Not much. So the deformations are going to be very small within this. So the deformations here are going to be almost nothing. But what's holding this back from moving away? Right? So now there is a lot of stiffness. What is that going to do? Attract a lot of force. But they've pulled the load out of these. Okay? So that's the whole idea. And usually they're several times stronger, stiffer and stronger. That doesn't mean, this is an extreme case I'm talking about, but reality can get quite close to this when you're looking at short to medium span bridges with wide decks. We've done lots of retrofits where it's very tedious to go and retrofit the columns. There are a gazillion deficiencies with them. What we go is we go and retrofit the abutments and we make them very strong and stiff. And we do that in cases where the deck aspect ratio is helping us. And we make them work as a stiff diaphragm. You might have construction joints from span to span. We go in and we put link decks, so we put continuity into the deck. But guess what? Now it can't do that. It can't just open up at the joints. Won't throw load into your piers at all, or very little, below the threshold that they can take. So the load is going to the abutments. The trick is, can you make them that stiff and strong that they won't fail? And if you can, and we've done it successfully on many projects, it's a really good opportunity to get away from mucking around in here. There may be traffic underneath, there may be lots of issues. You can get away from it. So our code, it's basically based on Caltrans. Excuse me, it gives you an abutment stiffness that you can utilize. And here are the two cases. I showed you two kind of abutments. One was a seat abutment that had a gap between the back of the girders and the back wall. So what happens there is you're going to have to close the gap first. So this is the gap, and only then do the two things come in contact. So you can use this effective stiffness rather than the gap in a response spectrum analysis, or you've got this. You can do that. Now what happens again, if I take, say, the second example, and you run your analysis by using this stiffness K. You run your analysis, and you see, oh, there is very little deformation. You're super happy, this is working. And then you look at it a bit more closely. You look at the abutment spring that you've put in there with the stiffness, and it's showing a force up here, and this much displacement, fine. but it's showing a load up here. Well, the abutment cannot develop that much load. So what you just got is artificial, right? So what do? You then say, okay, I'm going to correct for it. I'm going to use this displacement, but I'm going to use this force level because my force level cannot go beyond that. My soil at the back is yielding that. So I cannot provide more force than this force. Then I do my second iteration and I end up here. Now I've softened the stiffness. I'm going towards a more realistic behavior. And when you get here, you find that, yeah, it's not that far up, but now it's following this slope, it's here. And you say, well, I haven't quite converged yet. You do another one, and you do this. And when you come up with it, you say, well, I've ended up kind of here, and I correct one more time. And for all intents and purposes, now I've converged. Usually, in my experience, 2 to 4 iterations are enough to converge, because in response spectrum analysis, there is no potential within the program to give you corrected stiffnesses. That only happens when you run pushovers by inputting proper nonlinear springs. You can't do that in a linear analysis. So now this is your appropriate stiffness because the load cannot go beyond that. This is your delta. So your abutment has moved maybe 30 mils. Can your columns tolerate that, or has it gone beyond the displacement capacity of the column? If it has, you either need to do something with your column now, or you need to go stiffen up and strengthen your abutment, and there are ways of doing it, putting shear keys or putting supplemental piles and attaching it to the original, or you do both. Okay, but you can't just use this. So this is a very good starting point, and the code, if you read through this, it says, yeah, you can use this initial stiffness. It gives you this initial stiffness, but that's just giving you this initial stiffness line. Okay? And if you multiply it by the width, then you get the total stiffness of it. But you can also come up with the PBW or the P-dia, which is the diaphragm abutment. As soon as your force goes beyond that, you are in a situation where you have to iterate. So you cannot go beyond this line, and you have to subsequently iterate to come up with that value. But you will see that that helps in a big way. So very quickly, I'll show you, here's my abutment stiffness. I've put 4,300 as a starting point. So here we start, okay? No longitudinal abutment stiffness model. I've got all the stiffness just coming from my bent. I've put rollers at the ends. Well, guess what? My period is 2.6 meters, because this is like 100 meters or plus bridge, long bridge. And all it's got is 2 columns bending in single curvature. That's all my stiffness. That's what I'm getting. Now I put the initial abutment stiffness, which is 4,300 something, and my period drops from 2.6 to, look how drastic this is, 0.63. Day and night difference. Because I put in a really strong, really high stiffness. Okay, fair enough, it doesn't move much. But what I found with that was that this was moving, the force that that spring was getting was way up there. So I'm not showing the intermediate iterations, but once it's converged, the period is 1.97. We started at 2.6. So there is a considerable drop in your period, which means you have a considerable drop in your displacement as well. It's a stiffer system. And so when you have less, you're going to throw less load here. Okay? So it's trying to balance out the force flow. It's trying to see how much you can take in the abutment, how much you can share at the piers. If you throw everything at the pier, it may be problematic. But then again, don't just go with the first stiffness without checking this. Now, if you go with the first stiffness and your force level is here, which is below that point, do you need to iterate? No, because you haven't gone beyond its elastic capacity. So that initial stiffness assumption is accurate. It's appropriate. Okay, so 90% mass for this one here, you can see in the very first mode, you get 99%. And in the very first transverse mode, you get 82%. And then the seventh mode gets you to 93%. So really, I have been involved with some complex bridges where we've had to run over 200 modes, 500 modes to capture that 90%. And then on a simple bridge, this is again telling you that this structure is really behaving in both directions as a single degree of freedom system. The first mode for each one of the directions, principal directions, captures the entire modal mass contribution. So this is just showing you a quick calculation for the abutment. This is what I was showing you earlier. This is a semi-integral abutment, basically, so you don't need to put a joint here anywhere. These bridges are relatively maintenance-free because you don't have any joints. The water doesn't seep through. They give you a lot of benefit. You have to balance that against temperature and all that, because if your bridge is very, very long and it's jointless, when it expands and contracts, you're going to put in a lot of lock-in stresses. You've got to be mindful of that when you start locking everything in. It's a good idea generally, but the thought has to go a little bit beyond that. You can't just say, oh, I'm on a 200-meter bridge, I'm going to lock everything up, and then it could become problematic. So this is again just showing your first abutment stiffness is at 185,000 kilonewtons per meters. You run through the analysis. Now here's the thing. To model this appropriately, you've got two abutments. When the bridge moves this way, it only is resisted on the one side. The other side is moving away from the soil. Now in a response spectrum analysis, your springs are tension compression. They're not compression only. So as you're pushing into this wall, into the soil on this side, you have a spring that's going into compression, but you're also pulling on this other spring, which is artificial. That thing is moving away from the soil. There is no spring there. Okay, so in a response spectrum, one trick you can do is to go with half and half the stiffness on either side, so your total stiffness is the same. So in design office, we have to come up with these sort of rational shortcuts to make sure that we're not doing something that doesn't make physical sense, yet be able to use the tool. So because this is not a tool where I can use a compression-only element, i.e. on this side as it moves, it's just doing nothing, because it's once you have a thing, it's active in both tension and compression. So we go half and half, and we come up with the force. So you can see here that the force in the diaphragm is 1,544. And so this is the capacity of what the diaphragm and the soil together can generate. The demand from the software is 6,100 kilonewtons. That's almost 4 times. So you've overshot this point by a factor of 4. You're sitting way up there. That means it's not correct. So now we go and we correct it. So we take the displacement from there, we take the plateau force, we come up with a new stiffness. Now all of a sudden, my stiffness has dropped from 190 something odd thousand, or half of that, to 28,000 or 14,000. And now I come up with the same thing again, and I find that my next displacement is 117 mils, which is much larger than 55 mils, over a factor of 2. I go through about 5 iterations, and I find that now I'm getting very, very close. So 4680, 4265, I'm at about 184 mils. So from the previous iteration, which was 181, I'm at 184. Now I've converged. Okay, so we need to go through this. But if you were to just leave it, it would be a lot more. Okay. So these are the bending moments. So you look at this. This is about 13,600 kilonewton meters of the column demand of the base, without having any abutment stiffness. Okay? Now, when I go with the initial stiffness, it drops from 13,000 to about 2,000. a factor of 7 drop. But that again assumes that your backfill and the diaphragm can generate about 6,000 of this instead of 1,400 or whatever. So that's not realistic. And then when you go to converged, instead of 13,000 something, you're at 9,000. So your abutments are definitely helping you. That's a drop of about 40%. So your column sizes are going to be a lot more manageable. Okay, so let's take 10 minutes, but let's keep it as 10 minutes because we need to move into the next one. Okay?